Okay, welcome back, everyone. So the second talk will be by Fintzen from University of Bonn, and her title is Representations of p-adic groups and Hecke algebras.
Thank you. Thank you very much for the invitation to speak at this wonderful conference. And I really enjoy being back to Princeton, in particular after I was here remotely during the pandemic, which is definitely not the same as being here in person. I'm talking about representations of p-adic groups. There are some applications to p-adic arithmetic geometry, but I understand it's a bit further away than some other talks. So I try to make it accessible, but feel free to ask questions anytime. So P is a prime number, as we all know and like, I think. And some more notation, F will be a non-Archimedean local field. So F is either a finite extension of QP, or F could be the Laurent series over finite fields. And the field F contains a ring of integer O, which contains the uniformizer pi, or I think you here use var pi for it. And the residue field, so O mod pi O, is denoted by FQ. So finite field with Q elements. So that's the basic setup. And what's the main layout for this talk? It's denoted by G, and G is a connected reductive group over this local field F. So, for example, you can think of GLN, SLN, or symplectic groups, or orthogonal groups. Oh, right here. Whichever you like. If you're not so familiar with reductive groups, just think of one of these classical groups. If you love reductive groups, think of the most crazy example you can think of, like some forms of exceptional groups or so. But I want to assume that the group splits over time extension. Split over time extension of the local field F. So for example, units in a division algebra, they become isomorphic to GLN over some time field extension. So that's totally fine. And I think most examples you could come up with are totally fine. All right, so that's the main object. And what is the main goal? So the goal for this talk, and also the goal that a lot of mathematicians worked on for the last more than 50 years, is that we want to understand and ideally describe rather explicitly the category of all the smooth representations of our p-adic group G of F. So I call this group the F points of G, usually p-adic group, even if we are in the equal characteristic case. It carries a topology, and we look at the smooth representations. So those representations said that every vector in our vector space of the representation is fixed by some open subgroup. So that means every vector is fixed by something large, but still the representation itself is usually infinite dimensional, but it's something that is rather well behaved. I didn't put the coefficients down yet. Let me say that I want to look at representation as complex coefficients, so maps from the group into the space of automorphism of a complex vector space. A lot of things also work FL bar, but as we learned, L is not that appreciated here apparently. Well, I guess C not that much either, because that's isomorphic to QL bar. So a lot of results work modal. I might restrict to C just for simplicity. But if you're interested, don't hesitate to ask. So that's the big goal. That's what we want to achieve. And there are two steps to this goal. And the first step is that there are so-called, or there are building blocks for all representations. And these building blocks, they are called supercuspidal representations. Let's see, supercuspidal representations. And what do I mean by building blocks? I mean the following fact, to make this more mathematical, which says that if pi is an irreducible smooth representation, I will drop the adjective smooth, but all my representations are smooth. If pi is an irreducible smooth representation of our p-adic group, then it can be obtained from the supercuspidal via parabolic induction. So then there exists some parabolic subgroup inside our group G, which might be equal to G, So that's the product of the levy and the unipotent radical. M means block diagonal for me in the case of GLN, so that's M, and N means upper triangular. That's the N. And so there exists a parabolic subgroup together with sigma as supercuspidal representation of the Levy subgroup such that we can obtain our representation pi inside the parabolic induction from this parabolic subgroup to the whole group of this supercuspidal representation sigma, or if you like, sigma tends to 1, it's the extended trivially on n to representation of the parabolic, and then induce. So that means every this representation occurs in the parabolic induction of a supercuspidal. So if you want to understand all representations, the first step will be to understand supercuspidals, and the second step will be to understand how to get everything from these supercuspidal representations. All right. So that means problem 1. Now I realized I marked this side, but I didn't mark that side here. How far down can I go because of this dot?
Another like 6 inches.
So how far over? I'm going.
I can certainly read everything outside of that box.
Looks good. Okay. So the problem 1 is to construct all supercuspidal representations. And so here's the spoiler, the vague answer. And the first part of the talk will be to make this more precise. The vague answer is we can do this under minor assumptions. Minor assumptions. And I'll make this more explicit in the first half of the talk and give you an idea how these representations look like. So let's just assume we have solved problem 1. So then we need to understand how to get everything else from that. And so that's via the so-called Bernstein decomposition. And the observation of Bernstein was that if you take the category of all smooth representations of your favorite p-adic group, G, then this decomposes into blocks. And these blocks are indexed by Levy subgroups together with supercuspidal representations. So I take a product over pairs consisting of Levy subgroup and supercuspidal representation thereof up to a certain equivalence relation. And what is the equivalence relation? Let me start by explaining the equivalence relation and then what these blocks are. So we say that M and sigma are is equivalent to another pair if the other pair is just the conjugate of the initial pair. So you just conjugate your Levy and then you have to conjugate what you put in there. Let's see, I'm a bit jet lagged. I hope that works. If I put this in, it cancels, yeah. So you can just conjugate everything by an element G inside your p-adic group. Or the other thing that you're allowed to do is you can twist your representation by some chi being an unramified character. Unramified means it's trivial on compact subgroups. So you can take a character that is trivial on all the compact subgroups and twist it. That's another thing you're allowed to do. So that's your equivalence relation. It's a bit technical, but all it really ensures is that this decomposition works. So you can actually just forget about that again and just focus on what actually these blocks are. So these blocks, well, they're called Bernstein blocks. Bernstein blocks. And what are they? So I said the fact was up here that every irreducible representation occurs in the parabolic induction. And so we just divide the category into these blocks coming from where do we induce from. So this block indexed by M and sigma contains So this contains all representations whose irreducible subquotients. So the representation might not be irreducible, so we compose it into irreducible subquotients, and all these irreducible subquotients are contained in the parabolic induction from some parabolic p prime of some supercuspidal sigma prime, where p prime is equal to m prime, and then this m prime sigma prime should be equivalent to m sigma. So maybe this is a bit confusing on first glance, so let me just rephrase it. How do we get the Bernstein block? We take our Levy subgroup M and our representation sigma, parabolically induce that, and take everything that we can find inside this parabolic induction. And then we do this for everything else in this equivalence class, so by conjugating the Levy and representation around. And if we collect all this information, we get a Bernstein block, and these are really the blocks of the category. You can't decompose them any further. So that's how we then can understand the whole category. So now we assume we understand what these representations, these supercuspidal representations are. And so we need to only understand what are the blocks indexed by them. And so that's the second problem. So problem 2 is understand the Bernstein blocks. So understand Bernstein blocks attached to Levy together with a supercuspidal representation. Let me maybe first give you an example to carry around. Particularly if you see it the first time, I think it might always be helpful to see some examples. So let's just take G to be SL2, my favorite example for talks. And well, what's the first? Well, what are the levies of SL2? There isn't that much interesting. It's either SL2 or a split torus. So let's say the first case is that M is equal to G, so equal to SL2. In that case, sigma is a supercuspidal representation of M, which is the same as G. So we just have a supercuspidal representation of our group. And in that case, the corresponding Bernstein block consists of, let me just say what the objects are in this category. The objects are just the representation sigma itself, sigma plus sigma, sigma plus sigma plus sigma, and so on. Arbitrary direct sums of the irreducible representation of the supercuspidal representation sigma. So there are no interesting extensions that happens. It's just sums of sigma, and then the endomorphisms are also rather boring because the endomorphisms of sigma is just the complex number multiplying by complex numbers, so you can use the rest from it. The second example is that the Levy is equal to the torus, so the diagonal matrices. I use notation in the same way as Charlotte did. This is an algebraic group. Here are the points. I think it's clear what I mean. And let's say we take a sigma. Now we need a supercuspidal representation of a torus. So what does actually supercuspidal mean? I never defined it for you. I just said everything else embeds into a parabolic induction of supercuspidal. And the supercuspidal ones are those that do not embed into a proper parabolic induction. So that means the only case to embed it is for P equals G into a parabolic induction. And so for a torus, there are no parabolic subgroups, so all representations are supercuspidal. So you can take any representation you like. And in particular, you could take sigma to be just the trivial representation. And then you can ask, what is the Bernstein block corresponding to this torus together with the trivial representation? And well, how do we obtain this Bernstein block? I said we just take the parabolic induction, the parabolic containing the torus would be the Borel, so just matrices of the triangular matrices to the whole group of the trivial representation. And you can check that this contains the trivial representation. So the trivial representation embeds into this. You can also check that there's an irreducible quotient, and that's called the Steinberg representation. And this is a non-trivial, non-split exact sequence. So that means if we want to see what's contained in here, we have to collect everything contained in this parabolic induction. So it contains the trivial representation and the Steinberg representation. And you already see that this block is more complicated than the previous block. So I will not tell you more than that, just say it is more complicated and it has a name. This block is called the principal block. And so one consequence of this talk will be that at the end of the talk, I hope we will understand what the principal block is. All right, so that's an example of how these Bernstein blocks look like. And we see already that there's something interesting happening. It's non-trivial in the non-supercuspidal case. And we want to understand these Bernstein blocks. And here's the vague answer, the spoiler of the talk. And this is joint work in progress with Jeff Adler, myself, Manish Mishra, and Kazuma Ohara, which is the following vague statement. If you take an arbitrary Bernstein block, then this Bernstein block turns out to be equivalent. So this category is equivalent to another category, which are obtained by just putting a zero everywhere, which you might find a bit disappointing because I substituted one object you don't know by another object you don't know. But the whole purpose of doing that is that, what is this? So this, and I will define this later in the talk. These are depth zero representations. We have already seen this in Charlotte John's talk before. So these are representations that correspond to representational finite groups of Lie type. And the whole point is that actually this block here is rather well understood. So this block, in the case of depth zero representations, was already studied much earlier. That was studied by Morris in the early 90s, and he gave an explicit description of this block in terms of modules over a rather explicit Hecke algebra. And so we reduce arbitrary blocks back to this depth zero case where one knows the structure, and therefore we also understand the structure of arbitrary blocks.
But Morris is only for classical groups, right?
Morris, the comment was Morris is only for classical groups. No, Morris is for general groups. What Morris actually does is he studies only a union of Bernstein blocks, but we generalize Morris results. So I'm hiding a few details. So I also need to put our initials there to be very precise, but roughly the idea is that Morris already knew how to deal with that case. So that means one answer is that as a consequence, we'll understand how these blocks look like, and I will show you how they look like. Another consequence is that you can reduce questions about the representation theory of p-adic groups back to questions about representations of p-adic groups of depth zero. And questions in this setting are often much easier or are already understood because these are representations of finite groups, roughly speaking, where, well, this is a very complicated story, but a lot of things are easier there, already known, or there's, yeah, much more hope to be able to understand things. So that's the big outline. Maybe I should have said also a few words about why we care about these representations of p-adic groups. Why do we care about making things explicit? Well, if we want to study these representations of p-adic groups, it's really helpful to have some explicit understanding of them. So there are tons of applications within the representation theory of p-adic groups, but there are also applications beyond. So if you want to study the local Langlands correspondence explicitly, you want to write it down explicitly. If you want to study the categorical local Langlands correspondence, having an equivalence of these categories of blocks reduces the problem essentially up to additional work to depth zero, where it's work in progress. I think by Shinwen. And what else? There are also applications to automorphic forms. You can obtain constructions of the global Langlands correspondence as some consequences of understanding better the representations of p-adic groups. There have been applications to the construction of p-adic automorphic forms using these explicit supercuspidal representations. And I'm sure.
Assumption on P for this equivalent.
I have assumptions on P. Yeah, this is just a vague answer, so I will make it precise towards the end. If you assume P doesn't divide the order of the Y group, this holds on the nose. Otherwise, I have to add more details that I will add throughout the talk. So assume P doesn't divide the order of the Y group, and this holds as written. Any further questions at this point? So then let me, wait, or maybe I should have said, wait, answer to problem 2. All right, then let me start with problem 1 and afterwards come to problem 2. So let's talk about the construction of supercuspidal representations, but also of types. Even though I haven't told you yet what types are, I just don't want to draw the picture twice. So the picture for types will be the same as for supercuspidal representations. So I will tell you afterwards what types are, and then I will tell you everything we did before works for types as well. So the construction of supercuspidal representations is known in the following cases. It's known for GLN for a long time. That was done 30 years, it was finished around 30 years ago by Bushnell and Kutzko, but the story started much earlier by work of Hauer and Moy, and a lot of people worked on that as well. In terms of classical groups, if P is not equal to 2 is also solved. That was done by Sean Stevens around 15 years ago, maybe by now. Inner forms of GLN are also dealt with. GLN, that's thanks to Sean Stevens and Vincent Sécher. So I guess I got the alphabet wrong, Sécher and Stevens. And so all these cases rely on really the structure of GLN. They use the GLN as n by n matrices, and you have an n-dimensional vector space attached to it. And then the classical groups, which are just fixed points of involutions inside GLN, try to redo the construction for GLN and making everything invariant under the involution. That's the rough idea. It's much more complicated than this, but that's the rough idea. And so what I'm really interested in is to do this for general groups G. And I want to draw a picture that some of you might have seen before, but others not. So I'll keep it rather brief and will not give an exhaustive account of all the literature, but just a big overview. So I think it started, it's fair to say, let's see, where do I draw and where do I write? Let's draw and write here. Big breakthrough happened with Moy and Prasad in 1994-96. What did Moy and Prasad do? Well, I said that every representation that we consider is smooth, which means every vector in the vector space of this representation is fixed by some open subgroup. But we don't know which open subgroup. And so what Moy and Prasad did is they defined a filtration of open subgroups that were large one, and then smaller and smaller and smaller ones. And now if you have a representation, they then just wonder, okay, how far do I have to go down this filtration until I have fixed vectors? And that's what they call depth. So Moy and Prasad introduced the invariant, which is called the depth, which is either a 0 or a positive real number. And, oh, I hope it's visible. That is the depth. And what Moy and Prasad did is they studied the depth 0 representations. So let me draw in this direction the prime number P. So this is P, our prime number, because some results depend on what the prime is. And Moy and Prasad, they studied these depth 0 representations. So that's what Moy and Prasad did. And also Morris roughly around the same time. Maybe I'm writing it twice. Morris roughly around the same time, 93, 99, using different methods. So they studied the depth 0 representations. And then the next question was, how do we get deeper down here? There are all these positive representations. How do we construct them? And so that was the first, I think, general construction happened by Jeff Adler in 1998 in his PhD thesis. And that was then vastly generalized in 2001 by JKU. And this construction by JKU That provides us with a lot of representations. Let me just draw them as circles. So there are a lot of representations here that they constructed of positive depths.
Can you use brighter chalk? It's a little hard to see in blue chalk.
It's a little hard to see. Is green better?
Got it somewhat better.
Well, that's essentially all I'm drawing. So I'm just drawing circles. Or maybe what I should do, because people know me for this, I should draw a fish. Because Margarita told me he thinks of representations as fish that swim in an ocean. So these are the representations that we need to find. And so Adler, oh, I'm not sure that's getting better. Adler and you, they constructed a lot of them. JKU's construction is a construction that is the most general known today for general reductive groups. It's the one that Charlotte Chan also referred to in her talk. It's the one that people use when they try to do things with an explicit construction, because you can really work with it. It's something hands-on. Maybe I should also put my initial there for fixing a few gaps that occurred later in providing an alternative proof.
Sorry, what's the definition of depth again?
The definition of depth is, the vague definition is that 1% define a filtration of compact open subgroups, which Charlotte Chan denoted by GXR. And the question is, how far do we have to go down in this filtration until you get fixed vectors? So the depth is in the smallest integer r such that if you go to depth r plus, that is not true. So that's the depth r.
You've defined depth, but you said that depth depended on a positive real number.
Yes.
So, but there you said integer. So,
Sorry.
so like, what's the difference between like GXR plus and GXR plus 1, for instance? Like,
GX. Sorry, Damien, I didn't meant to go into that much detail. It's just the union over all the GXS for S greater than R.
yeah, but
So
wouldn't that just be GXR plus 1?
It would be GXR plus a very small epsilon, because you might have jumps not just at integers, but also at, say, half integers, quarter integers.
Oh, you haven't defined what those are for.
I haven't defined for you at all the Moivre-Sat filtration is the answer. I sometimes give talks in which I do define it, but it doesn't really matter for what I want to do today, so I decided to not do it. But I'm happy to give a mini lecture afterwards to anyone who wants to learn more. So this is, I give you 5 seconds and then I erase that so that I have space. I think that was 5 seconds. All right. And well, I said use construction is vastly used. So the question is, what can we get out of that? And then in 2007, I hope Brad is readable, otherwise, Julie Kim actually proved that this is exhaustive. So everything comes from use construction. If we are in this region where P is very, 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 very large. So in this region here, everything comes from use construction if the characteristic of the field F is equal to 0. So Julie Kim showed that use construction is exhaustive if P is very, very, very large and the characteristic of the field is 0. So yeah.
I assume the lower bound for P depends on G.
The lower bound for P depends on G and also on F heavily in that case. Yes.
And is it effective?
Julie Kim writes down a bunch of criteria that you need to check, and it's non-trivial to check when they're satisfied. But for GLN, I think P greater than n times E, where E is the ramification index, should do the job, something of that sort. And then in 2021, I showed that use construction is exhaustive only under the assumption that P doesn't divide the order of the Weyl group. So if we're just in this region where P doesn't divide the order of the Weyl group, then we get exhaustion. And also we no longer need the assumption on the characteristic of the field. So we get everything from use construction just under the assumption that P doesn't divide the order of the Weyl group. So W is the Weyl group. So for GLN, that's just Sn. So that means for GLN, P has to be larger than N is the only condition. So that means in this setting, we know everything. And that's what we then also use to reduce everything back to depth 0. So we know everything of higher depths, and we want to reduce everything down to depth 0 eventually. And one more remark, let me see. Yellow, let's hope yellow is readable. So as I said, I'm skipping over a bunch of things. So for example, Rita and you constructed some representations of small depths that together with my own work and partial work of Bertromana and myself gives us some new representations of small depths here. And what I'm currently working on with my postdoc, David Schreen, is to construct new representations in the deeper zone for small primes P. So we try to construct all the representations that are tame to try to get a better handle of what happens also for the small primes. I hope that this will appear next year, so fingers crossed. Now it's on record. So that's what we get out of explicit constructions. I want to make a few remarks with how do these constructions actually work. So first remark is that all these representations are of the following form. They are all compactly induced from some compact mod center open subgroup to the whole group of some representation of it. So K is compact mod center open subgroup of our group GFF, and all the representations here are constructed via compact induction. So that means these are just functions from the whole group. So the vector space of this finite dimensional representation, V sub rho, that transform on the correct side via this representation. So f of kg is rho of k f of g for all k inside our compact mod center subgroup and G in our group. And moreover, we want these functions to be compactly supported. So it's rather explicit. We have this huge infinite dimensional space of functions. So it's roughly the space of functions on G mod K. So that's how you get this infinite dimensional vector space on which the group acts just via right translation. And let me maybe make this even more explicit by giving the example for SA2. Well, there are many examples you can give. Let me this time give a depth 0 example. So what we need a compact open subgroup. So let me just take SA2 over the ring of integers. That's a nice compact open subgroup. What can I do with that? Well, I can mod out all the matrices that are congruent 1 modulo the identity. So all the matrices of the form 1 plus bar pi O on the diagonal, bar pi O off diagonal. And well, if I write something like this, I mean determinant equals 1. I might not write this anymore. So what is this? This is just isomorphic to SA2 over the residue field. And here we go. We have our representation of finite group of Lie type. And now we just take some cuspidal representation of that. And we call this rho, just some cuspidal representation. As for example, constructed by Delin and Lustig. And so if we then trace through, we get a representation of SA2 that we can compactly induce. And then we obtain pi rho, just a compact induction from this compact open subgroup to the whole group of this representation rho. So cuspidal means that it's not coming from parabolic induction for this finite group. And so that's a depth 0 representation. It comes from a representation of a finite group of Lie type. And you can do this more general. If you want to work for G, if you want to take a general group, instead of SA2 of O, you would take what is called G sub X, the stabilizer of X in the building. What is that? Well, let me just say, this is just a maximal compact subgroup in the case that G is semi-simple, simply connected. Otherwise, you have to worry a bit about center and so on. But so think just of a maximal compact subgroup. So you take a maximal compact subgroup, and then you quotient out something smaller. So you quotient out what is called gx0 plus. And what is this? This gx0 plus is just the pure p unipotent radical that you quotient out. And then what is the whole quotient? This whole quotient here, this is just some group over the finite field, at least if G is semi-simple, simply connected. Otherwise, again, you have to take care of the center. So you start with a maximal compact subgroup, you quotient out the pro-p unipotent radical to obtain a finite group of V type, and then you compose, well, let me just go here with the cuspidal representation. And then you compactly induce. So, well, I don't have to write the same thing once more. So if this is K, you get the compact induction from K to the whole group of rho. And this is then a depth 0 supercuspidal representation of our group G of F. So what started as an example for SN2, I've now in yellow made very general. So general depth 0 representations are exactly of that form. So all the depth 0 representations are of that form, compactly induced from representation of a finite group of D type. So that's what Moy and Prasad did. Which that approach goes back. All right.
Sorry, and later in the talk, are you going to talk about what G0 is in the first vague answer you wrote down?
Kind of. I mean, I'm happy to tell you at the very end, but the answer might not be super satisfying. The longer answer is maybe for after the talk.
Okay.
The short answer is it is a twisted Levy subgroup of your group G, but which one is then more complicated? Well, I said remark 1. Let me not write down the second remark, but just say it in words. The construction of supercuspidal representations works mod L the same way. So everything I've done here works also mod L, if you like. All right. That was the construction of supercuspidal representation. That is the answer to problem 1. Now let's move to the second problem, which was to understand these Bernstein blocks. And we do this using types. What are types? So I said that.
Sorry.
Yes.
Question. So was this for depth also for you said this was depth 0?
Yeah.
What about the other ones?
What about the other one? Excellent question. So the other ones, all of them, so this part of the remark applies to all. All are compactly induced. But for the non-depth 0 representation, this K is more complicated. In particular, everything here is trivial on the 0 plus piece on the pro-p unipotent radical, and that means depth 0. So for general representation, it will not be trivial on this gx0 plus, but it will be more complicated. So you have to take something higher and higher depth. So that's a bit what Charlotte has done with her G sub R's. So that's where you induce from. You construct these bigger quotients.
Thank you.
More questions at this point? All right, types. Types are allowed to come on the stage. So I said supercuspidals are compactly induced from a compact subgroup, or compact mod center subgroup. The idea of types is to use compact open subgroups to also understand all the other representations. So let me give you the definition. So a pair consisting of K and rho. What is K? K is now a compact open subgroup of G of F. And rho is an irreducible representation of K. This pair is called a type, is called an type, and it's a type attached to a Bernstein block, so it's called an M sigma type. If the following happens, if the following are equivalent all irreducible representations phi of G of F. And what are the two things that should be equivalent for this pair to be called a type? The first one is that this representation pi is contained in the Bernstein block under consideration. So the Bernstein block attached to M sigma. And the second is that this representation, when restricted to this compact open subgroup K, contains this representation rho. Or in other words, you can also say that the space of K homomorphisms between rho and pi is non-trivial. So what does a type do for you? The idea of a type is that you understand if some representation is in the Bernstein block by just studying the restriction of this representation to your compact open subgroup K. So that's the idea of types, that we understand where in which Bernstein block we lie by looking at the restriction to K. And also, not only that, we have a nice application on theorem that then tells us how to understand the Bernstein block. So that's a theorem by Bushnell and Kutzke from 1998, who introduced these types, which says that suppose we have a type, so suppose K and rho is an M sigma type, then they say, then we have a better understanding of the Bernstein block. More precisely, they say that then the Bernstein block corresponding to M and sigma is isomorphic to modules over some explicit algebra. It's isomorphic to modules over a Hecke algebra attached to K and rho. Right unital modules to be precise. And what is this H of K rho? This is by definitions all the functions. You might want to compare it with compact induction over there. All the functions from the group, now not to the space of rho, but to the space of complex endomorphisms of this complex vector space V rho, such that, and now the transformation happens on both sides, such that F of K1 G K2 is equal to rho of K1 F of G rho of K2. So you can now pull out the K on both sides. So for Ki's inside K and G inside G. And as before, F should be also compactly supported. So that's the Hecke algebra. Well, this is just the vector space, but it contains an algebra structure via convolution. So it's a explicit integral you can write down to convolve two functions. And that's the Hecke algebra that's attached to a type. And whenever you have types, then the Bernstein block is equivalent to modules over this Hecke algebra. And when do we have types? Well, we have types exactly in these cases. Types are known for GLN, classical groups, if P is not equal to 2, inner forms of GLN, and for general G if P doesn't divide the order of the Y group. In all these cases, we know that there are types, so we have explicit constructions of K and rho, and then we also know that the Bernstein block is equivalent to modules over this Hecke algebra. So that means in order to obtain this solve the second problem to understand the Bernstein blocks, what we now need to understand is what are these Hecke algebras. So that's the remaining task to be done. Let me make one more remark. Another way to define the Hecke algebra, depending on what you're more comfortable with, would be to just say it's the space of G, endomorphisms of the compact induction from the compact group to the whole group of your representation rho. So now we need to understand what the Hecke algebras are. So here is the first result from in 1993. Morris gave an explicit description of the Hecke algebra. So now I'm sometimes putting the G in to clarify things because we don't need it yet. For the case of a union, you can ignore the union, a union of depth zero Bernstein blocks. So that means for a union of blocks of the form attached to M sigma, where the sigma here is depth zero. And I said you can ignore a union of because I didn't even tell you how to do this. So I put our initials there. That was the answer to Yuji's question at the very beginning, that Morris actually deals with a union, but you can ignore this. So assume we have a depth zero Bernstein block, then he gave an explicit description of this Hecke algebra in terms of generators and relations. More precisely, one can say that how does this actually look like? This Hecke algebra turns out to be isomorphic to a semi-direct product of the first thing is some twisted group algebra. So it's some group algebra of some group that is something that is more difficult to define with a small twist, semi-direct product with some affine Hecke algebra attached to some affine Weil group attached to the whole data and attached. And with some indeterminate. So what, like, let me maybe give you an example so that this is less understood. So, for example, in the case of G equals SL2, well, we had two cases there. Remember, I might have just erased that. So the first case was where M was equal to G, and in that case, our sigma is then the compact induction from K to G of rho. That's our supercuspidal representation. Let's say G of F. And in that case, a type would be just K and rho. So this is a type for G sigma. And in that case, the Hecke algebra corresponding to this pair is just isomorphic to C. Because it's the endomorphisms of this irreducible vector space, which is just C. And then you also see that modules over C is just what I've shown you before, the sum of sigma, sigma per sigma, and so on. So it's rather easy, that case. And the other case, B, was the case where M is the torus, and we had sigma to be the trivial representation. In that case, the type K rho would be, for example, Iwahori subgroup. So these are matrices of the shape OO, bar pi O, together with the trivial representation. And in that case, the corresponding Hecke algebra. Now I'm using the first formulations. These are just functions on the double coset G of F. Well, G is SH2, mod out on both sides by the Iwahori subgroup. And so this actually is an affine Hecke algebra. This is isomorphic to just a spaces element. It's T sub W, where W is an element of some affine Hecke algebra, which is defined to be the affine Weil group defined by two generators S0 and S1, with the only relation being that their square is 1. So that's at the vector space. And as relations, we have relations of the form TSI, TW is equal to either TSI W if we are in the length additive case, or otherwise it's more complicated, it's Q times TW plus Q minus 1 times TSIW. Otherwise. And so that's what I mean by an affine Hecke algebra. So this whole thing here is what I like to call H sub f of this affine Weil group with parameter Q.
Q is equal parameter or unequal?
Q is Q. I mean, there in this case, it's just the Q, the cardinality of the residue field characteristic. In general, these QI, there's one Q for each generator of our affine Weil group, and they are more complicated. They might be different for each generator. You might have a different one. And the general idea is now that arbitrary Hecke algebras always look like these types of Hecke algebras. Always this affine Hecke algebra, and then maybe some small perturbation.
Is omega sigma the R group?
Omega sigma is not quite the R group. It's a bit more complicated, and I'm happy to try to explain more after the talk. It would be impossible to define what this group is about, but it's roughly, the idea is this affine Weil group is attached to some affine root system. And in general, when you have an affine root system, you get an affine Weil group, but there might be a larger group that acts on this affine root system, and this omega part is the one that preserves a fundamental chamber. So this affine Weil group is the part that moves the fundamental chamber around, and this omega group is the thing that preserves the fundamental chamber. I just haven't told you what the affine Weil group is, because there's a limit to what I can say in 60 minutes. All right. So I'm about to erase the picture, which just says that we know everything if P doesn't like the order of the Weil group. All right, so now where are we? We know now how the depth zero Hecke algebras look like. And so now, as I already gave the spoiler at the beginning, we want to understand how everything else relates to this. So here's what Jeff Adler used to call a dream. This dream, I think the first version appeared already in Yu's initial paper, like a version of that. And I think the dream has been around since then, with some people believing in it, others not. And well, here we go. What is the dream? The dream is that everything relates back to depth zero. Let me now make this precise. So let's suppose now that K and rho is a type as constructed by JKU, but let me also add the name of Julie Kim there, because JKU constructed supercuspidal representations, and then together with Julie Kim, they actually showed that the same construction provides us types as well, that is exhaustive if P doesn't divide the order of the Weil group. Well, the latter part is what I showed you. So they showed that you get types. So let this be a Kim U type for some Bernstein block attached to some Levy and supercuspidal representation. Then the dream is that then there exists the following. There exists some subgroup inside G, which is a twisted Levy subgroup, which means it's a subgroup that becomes a Levy subgroup over some field extension. And then we have a Levy subgroup of this group, 0, some Levy subgroup. And then we have representation sigma 0 of M0, that is of depth 0. So we have the depth 0 representation of that. And
sorry, G0 is a twisted Levy subgroup and M0 is a Levy?
yes, M0 is an honest Levy inside G0.
So what's the definition of twisted Levy subgroup?
Twisted Levy subgroup means it becomes a Levy subgroup over some field extension. So it's a subgroup that when you base change to some field extension, finite chain field extension, in this case automatically, it becomes a Levy subgroup.
Okay, so and then M0 is a levy of some parabolic which is actually defined.
It's a parabolic of G0. Everything is defined over the ground field F. Yes. So now we have a depth zero representation of M0, supercuspidal. Supercuspidal representation of M0, that is depth zero. And that means we have a Bernstein block now for this G0 corresponding to M0 and sigma 0. And we assume that there exists, or not assume, that's the hope here, the consequence, that there exists a type for that. This pair is a type for that. Is a type for this Bernstein block. So that's the hope, that all this data exists such that the conclusion then will be that the Hecke algebra that we started with, attached to our type K rho, is actually equivalent to the Hecke algebra of this smaller group with the depth zero type. So that's the hope, that's the conclusion that we want to prove. So starting with a K and a rho, a type for an arbitrary Bernstein block as constructed by Kim and Yu. The hope is that there exists all the same data with zeros attached to it, such that the Hecke algebra we started with is equivalent to the Hecke algebra for the depth zero piece. So this is a Hecke algebra for a depth zero Bernstein block. So that's what we understand. Thanks to Morse. I said up there, that's what we understand.
By the national method, when you say equivalent?
Right.
When you say equivalent, you don't mean like some abstract isomorphism.
No, we write down a very explicit isomorphism here. I mean, so far it's a dream, but yes, in 3 minutes it will be a statement. And yeah, maybe also to say, I mean, as algebras, I mean, it's an algebra isomorphism. It's rather easy to show that there exists a vector space isomorphism. So the tricky part is to show that there exists an algebra isomorphism.
So this is all when P does not divide the order of one.
So far it's just a dream. No, so far, I said let K rho be a Kim U type. And if P doesn't divide the order of the Rho group, we know that every Bernstein block has a Kim U type.
Okay.
For general, if P is small, there might just not be a Kim U type.
I'm sorry, is the K0 and rho 0, is that just the intersection of K with G0 and the restriction?
Yes, the K0 is the intersection of G0 with K. The rho 0 is, you can't, I mean, rho 0, the rho is a tensor product of rho 0 with something of higher depth.
Oh, okay.
I can say more at the end about that. And so in particular, as a corollary of the whole thing, we would then get that the corresponding Bernstein blocks are equivalent to that setting, which means that in particular, in the case that P doesn't divide the order of the Rho group, every Bernstein block would be equivalent to a depth zero Bernstein. And so when is the dream true? So for GNN, that was already proved, maybe not in that explicit setup, but that was proved essentially already when the whole thing was set up. Let me maybe focus just on general reductive groups. So let me say, when is this dream true for general G? There have been various results for special cases, and particular classical groups have been studied a lot. For general G, much less has been done. In 1998, Alan Roach actually proved this in the case that the Levy subgroup M is equal to T, a maximal split torus. Sorry, a split maximal torus, that way around. So that means in particular the group G is split and the Levy is just a maximal split torus. And then recently in 2021, Kazuma Ohara has proven the other extreme. He proved the case where M is equal to G. So that means we have just a supercuspidal block, which for SL2 was rather boring. because there with the Hecke algebra is just C, the complex numbers. So we now have the two extremes, and so theorem or expected theorem, that's work in progress. Together with Jeff Adler, Mishra, and Kazuma Ohara, is that the dream is always true. That means we always get that arbitrary Hecke algebras or arbitrary blocks are equivalent to depth-0 blocks in the case of the ones constructed by Kim and Yu, which are all if P doesn't divide the order of the Weyl group. And hence the arbitrary Bernstein blocks are equivalent to depth-0 Bernstein blocks. So a lot of questions can be reduced to depth-0. And two more remarks to make. First remark is we actually work in a much more general setting than Kim and Yu, so that it can apply also to future constructions for small primes P. And the second remark is, in a minute, I won't say much about the proof, but let me just say that it was really crucial that we didn't use the construction of Kim and Yu as done initially, but that we used the one that was twisted by this quadratic character that Tasha Kaletha, Lawrence Spice, and I introduced, that Charlotte Chan already mentioned. So part of the proof was that we actually had to extend this quadratic character, this twist, because without the twist, the result is just false. So it was really crucial to use that. I think I should stop here, and I'm happy to answer more questions.
Yeah, are there any questions?
Could you give an example of such a triple G0, K0, maybe one of the examples?
I give an example of the triple. Any example you so
it will be that.
well, one example would, okay, let's see, examples. Say G is equal to SL2. So there can be many, well, there are many, so what could G0 in that case be? G0 could be, well, it could be either SL2 as well, if we start with a depth-0 representation, or it could be, well, the other option would be that it's a torus, which could be either T, which could be either the diagonal torus, or it could be an Tn, which is the an anisotropic torus inside SL2. So it corresponds
Rho is
to
depth 1, then what are the choices that you want? If rho is not depth 0.
if rho is not depth 0.
Yeah, if rho 0 will be depth 0, right? But
Rho 0, yeah. So if rho is not depth 0, then it has to, in that case, G upper 0 has to be has to be a torus. And then which one you get depends on the situation you're in. If you have, I mean, this one you might get if you have a principal series representation with the character being appropriate. And yeah, I mean, if you want afterwards, I'm happy to write down examples for everything. You can actually do this rather explicitly. And in particular, rho 0 would be just a character, because the only representations of tori are characters.
These Hecke algebras generally have like nice algebraic properties, so can you put like nice purely algebraic adjectives in front of them? Like,
What
I mean, such as noetherian or something like that, you know, just considered purely algebraically. Like,
I'm sure you can put a lot of adjectives in front of that, but I would need to, I mean, I haven't thought about it. So the structure is rather easy, because that's how all of them look like, times some finite p. So there should be a lot of adjectives that you can put in front of them as a consequence. So there, it's rather explicit. Yeah.
If you take the center of this Hecke algebra, what do you exactly get?
What do you get as the center? The short answer is I don't know. It's a complicated question what the centers are, I believe. I think from this, you can't immediately read it off. I think in general, it's a difficult question that people are actually studying. What are these centers?
Why do people expect that the dream is true?
Why?
Why did people expect that dream is true?
Well, I wouldn't even say that people expected. So there were two kinds of people: those who expected the dream is true, and those who claimed the opposite. In particular, like after I have talked about this result in the last few months a bit, and each time after I tell people about it, someone comes to me and says, "I have a counterexample; it can't be true." And then we tell this person, "No, your counterexample is not a counterexample," and we hope to have proven the result. So, why did people think there are counterexamples? It's mainly because they forgot to twist by this quadratic characters. If you don't put this in, there are counterexamples, plenty of them. So you really need that. Why did people think it is true? It just looks so natural. I mean, it's so easy to write down this as a vector space isomorphism. This might be even already in like a used paper, the basis of that. So you just want it to be also an algebra isomorphism. It's just, yeah, at least that's what we want. As I say, there are still people out there who believe that there are few Hecke algebras that can't be of that form, and I hope we can convince them by showing them our paper once it's written.
So how do you get rid of this union? How do you show that this union of blocks is actually just one block?
Oh, the union is still a union. What we do is actually we redo Morris' paper completely. So we redo everything in a much more general setup that applies to much more general Hecke algebras. So there is no short answer. The long answer is it's our 120-page paper.
And what is the formula for sigma 0 in terms of sigma?
What is the formula for sigma 0? Sigma 0. Well, sigma 0 is it has 0 representation, so this will be the compact induction of rho 0 from an appropriate compact open subgroup to the whole group. So you might want to ask, well, no, that's not quite true. I'm lying slightly because of the center. Somehow you extend for 0 and then you compactly induce. That's how you get sigma 0, but I didn't tell you what the compact open subgroup is. So you extend this to so rho 0 lives on a compact group, you extend it to a compact mod center subgroup, so you include the center, you extend it to include the center, and then you induce that.
Where do you use the twist?
The twist comes, so here's what Kim and you do. They take as an input for their construction G and G0, they take as the input already the rho 0, and then they take as the input some character. And from there, they construct a compact open subgroup together with a rho, let me call it rho KU, where this rho is the tensor product of rho 0, tensored with some kappa. And this kappa is built from this character phi. And so now, what is so that's the K rho and we start with, so this is what's called rho. Now I have to tell you what is K0 and rho 0. Oh, rho 0 is bad. Let's call it rho 0 KY for Kim and you. And so now our K0 is actually, well, let me add. So I said the input is the rho 0 from Kim and you, together with, well, this lives on the compact subgroup K0 and then this character phi. And so our K0, well, it's just their K0. And what is our rho 0? Our rho 0 is the rho, it's the rho 0 that Kim and you take as an input. But now comes the twisted by the epsilon FKS, Fintzen spice. So that means if we want to get from the K rho to this K0 rho 0, it's kind of already provided by Kim and you, reverse engineered, but we have to twist it with this quadratic character here. So that's where the quadratic character enters.
Any final questions?
Could you explain the construction of M0 for the case of GLN?
Can I? So I'm just thinking, I want to say only something short and can tell you more later because people want to have lunch. So, what can I say? The G0, well, you didn't ask me what G0 is. The G0 is a product of some GLNs over some other fields inside G. And M0 is a subgroup of G0 that has the property that, okay, there's secretly also a point underlying in the Brett-Tietz building, and it has the property that the reductive quotients of M0 and G0 agree. That might not be very satisfying if you haven't heard these words before, so I'm happy to actually give you a longer explanation afterwards while everyone else can have that.
Okay.